are all given at the leaves of the decision tree. So how do we learn these decision trees? All right, we have this data structure that's pretty straightforward. How do we learn them? The standard approach is a greedy method. And, you know, believe it or not, decision trees were first. Anyone want to take a guess when decision tree algorithms were first formulated and published? Any guesses? 50s! Right. Do you know who? No. Psychologist named Earl Hunt. And Earl Hunt was interested in modeling human concept learning. And humans are memory impoverished compared to computers. And so they are biased to form. About the only thing you can do with any kind of non-trivial classification task, or a human can do, is to use a greedy method to learn concepts. And so this idea was initially proposed by a psychologist. It was not really picked up and studied thoroughly until the late 60s and 70s, at which point it became sort of a, by the 80s, it was kind of a, it was still not looked at very much by machine learning people, who didn't really rise to any kind of dominance in AI until the early 80s. But by 1980, it was, or the mid 80s, it was certainly, it had been resurrected as a very popular method that machine learning people were looking at. And there's all kinds of variations to this, some of which we'll talk about. But this is the greedy method. I call it hill climbing here. We'll talk about later in a lecture why I call it hill climbing. This is pseudocode. We've got 3 arguments to top-down induction of decision trees. We've got a set of training data. And the book talks about training data. Training data is labeled data. So a vector, like characteristics of a movie, and a classification. Doug liked this, or Doug did not like this. And you might imagine that for something like a recommender system, this kind of algorithm would be run on each one of us. Okay, so that we each have our personal, our own, might have our own decision trees. We're going to be growing the decision tree from the top down. And so we need a function that tells us when to stop growing. And I won't explain the parameters here. They'll become perhaps clear later. And we also need a selection function. And the purpose of the selection function is to choose what attribute I should select at each step in growing the decision tree. Why is Ebert the root of this decision tree? Well, it's probably the root because it is the most predictive. If you could only pick one attribute and test values along one attribute, Ebert would probably get you the farthest in understanding this individual's watching behavior. That is, all by itself, Ebert, in the set of possible attributes or variables that you could choose, does the best at predicting what this individual might like. That's why it was chosen. Why was this node chosen as the root of the left subtree? This node was chosen as the root of the left subtree, presumably because within this context, within the context of Ebert not liking it, this is the most predictive single feature of what I might like in the context of Ebert not liking it. Siskel was chosen here because this may be the most predictive attribute of what I might like in the context of this subtree, that is, things that Ebert likes. Okay, and you can recursively apply that same idea in building the decision tree. So of those things that Ebert likes and Siskel doesn't like, suspense within this subtree is the most predictive, perhaps, of things I might like. And so we'll come back to this idea of recursive decomposition later, but It is one thing that makes decision tree learning and other kinds of machine learning very powerful, this notion of recursive decomposition. That is, different parts of the data may behave differently using different patterns. And decision tree gets at this idea by breaking the data up into subsets. Each subset may follow or manifest different peculiar patterns within that subpopulation. And decision tree induction is going to make that clear. So what I do is I have this data. If the data is such that I decide I want to terminate the algorithm, then I simply return a classification node. A popular way of deciding when to terminate is if all the data that you're looking at is of the same class. So all the data in this set are things which were liked by the viewer, then the algorithm really has nothing to discriminate. There are not multiple classes to discriminate. And so what would it do in the case where all the data were in the same class? It would simply return that one class. Now, it's pretty unusual that a viewer would like all movies. But remember, this is a recursive algorithm. And so as we're decomposing the data, we're going to be separating out data based on earlier decisions in building the tree, and we will get to subsets of the data that are members of the same class. And when we get to those levels, we're simply going to terminate and return a class that's represented in that data. If I don't terminate, though, if there are things to discriminate, and we'll come back and talk about that termination function later. If there are things to discriminate, then I'm going to select what I hope is the best variable or attribute present in the data that's going to best determine what the values are going to best determine and separate what are members of one class versus members of another class. And what I do after selecting that best attribute, so for example, if we're looking at that earlier example, Ebert on the first pass might have been the best variable here. And what I do in this case is I return a tree whose root is the best variable, Ebert, and I make recursive calls for each of the possible values of Ebert. Ebert didn't like, Ebert did like. I separate, I don't show all the arguments to TDIT here, I only show the data. And what is the data that gets passed to this recursive call? It's all the data in that initial argument in which the value of the best attribute is the one that I'm branching on here. So this would be all the data. If this is Ebert, this would be all the data, all the movie descriptions that Ebert did not like. This other branch would point to the subtree that was created through this recursive call, and the recursive call would be made only on the data that Ebert did like. Okay, so I'm taking this initial data set and I'm partitioning it into subsets. I'm calling TDITD recursively to build the subtrees there, and then I'm going to link the subtree that is built through this recursive call with this node as its root, and this subtree is going to get returned, and these are going to be made siblings of this common root. And then this is going to get returned as the outcome of the entire algorithm. And again, you can imagine that you're going to be building this tree from the top down, and that as you return these nodes, you're returning actually roots of subtrees that are going to get spliced into larger trees. This is not the only way to learn a decision tree. The greedy approach is not the only way to learn a decision tree. It might be more or less the only way humans could possibly learn concepts like this. Nonetheless, and we'll talk more about concepts like this in a moment, or towards the end of the lecture, because decision trees learn disjunctive concepts, concepts that are not described by a simple conjunction. Professor Wixwell once came to McGill to talk about the meaning of life, and he literally met the meaning of life. And so he engaged with the students on, give me a definition of life. And students were throwing out all these characteristics that they thought defined life. Reproduction, animation, the list went on. And Professor Wixwell was saying, no, there's some exceptions to that. There's some exceptions to that. My question to Professor Wixwell, because I have worked with decision trees before, does the concept of life have to be conjunctive? And he said, yeah, it has to be conjunctive. Why? Because the discussion would vanish at that point if it could be disjunctive. But disjunctive concepts are more powerful than conjunctive concepts. That is, life can be defined this way, or this way, or this way. Maybe it can't. I don't know. I don't know whether the meaning of life is disjunctive or not. It turns out humans are extremely biased towards conjunctive concepts, though. You ask somebody to define something, and it's almost always going to be a conjunction, unless you push them to define it as a disjunction or something else. But that was an interesting aside. So let's see how this algorithm, this greedy algorithm, might work on this data set. Here we've got 4 attributes or variables, and if you haven't noticed already, I'll go back and forth between variables and attributes, each with values. Again, these are all binary valued variables. The class is binary valued as well, C1 and C2. You can think of this as training data. We're going to be building our decision tree based on this. In this case, the algorithm is going to look at this data. And based on this data, it's going to choose the best variable. We'll talk in a moment about how that best variable might be selected. It's going to be intuitively selected so that it's informative. So that if I look at the values of that best variable, I tend to get reasonably close to either I get a perfect predictor or I get close to a perfect predictor. So for whatever reason, I've chosen or decided that V4 is the best predictor in this set, the best attribute in this set. And intuitively, the reason might be that, one, there is no perfect predictor in this set. When V1 is 1, sometimes it's C1, sometimes it's C2. When V2 is 1, sometimes it's C1, sometimes it's C2. When V3 is 1, sometimes it's C1, sometimes it's C2. And when V4 is 1, sometimes it's C1, sometimes it's C2. But we might have selected V4 because for the most part, when V4 is 1, 3/4 of the time it's associated with C1. When V4 is -1, 3/4 of the time it's associated with C2. And so there are no perfect predictors, but V4 seems to be a pretty good one. It takes us a step towards the right direction of getting a good predictor. So I choose V4 as the root of the tree. And then I separate out the data along its 2 values. This 4 just represents the number of instances set down each branch. And this vector just represents one of these vectors here where I've got -1, let's see, minus 1, minus 1. Let's see. I think this is it. Minus 1, minus 1, 1, minus 1 is a member of C1. So that's one of these vectors, and then I've got 2 other vectors. 3 of the instances here are going to be associated with C2 because in this case V4 equals minus 1. And then this data over here is associated with all instances in which V4 is 1. But in top-down induction of decision trees, I'm going to recursively make the recursive call on the left branch first. So there's the case from the last one. And for whatever reason, I decided within this subset of the data, V2 is the best predictor. In the case of V2, V2 at this level perfectly discriminates members of C1 and members of C2. Within the context of V4 being -1, V2 being -1 is associated with only C1. V2 being associated with or having a value of +1 is only associated with V2. And so at this point, assuming the termination function is as I described earlier, that when you get to a pure level in which all the data is a member of one class or the other, I simply return a classification. So that when you actually use the decision tree, and if you make it down to this node, you'll predict C1. Likewise, I am over here, and next I do this recursive call. The termination function, again, if the termination function is always members of the same class, it's satisfied, and I return C2, a classification node that is representative of, or gives a prediction of C2. So I've got this part of the subtree built, and now I turn my attention to the other subtree, and I decide within this context that V3 is best for whatever reason. And when I divide on V3, if I come down to look at -1, the instances with V3 as -1 are both associated with C1. So I build a class node after making that recursive call. You'll notice that in the case of this other branch, though, it's not pure. And that is, there's one member in which V3 is 1, member of class C1, and another instance of this subset has V3 equaling 1, but member C2. So this is not pure by the, and the termination function that I've talked about would, in general, would not, would continue decomposing. And here I decompose and I choose V1, and now I have pure classes. When V4 is positive and V3 is positive and V1 is negative, everything is in C2. Similarly over here, when everything is positive down this path, everything is a member of C1. And so that's my termination condition. And this would be my final tree in which I could make subsequent predictions. So if I only know V1 through V4 and I don't know the classification, I would run it down this decision tree and I would get an answer. Now there's lots of different ways for selecting variables as the best variable within the context of data. And the book actually talks about this in the reading that you went through. It talks about it in one of the earlier sections. It talks about information theory. And it talks about the log of probabilities. It turns out the probabilities it talks about are all power of 2 probabilities. So you have 2 to the -1, 1/2, 2 to the -2, 1/4, 2 to the -3, 1/8. And it talks about the log of the probability in information theory corresponding to this idea of the number of bits necessary to encode a message. This is a theoretical value because not every probability we will encounter happens to be a power of 2. Not everything we encounter will be 1/2, 1/4, 1/8, 1/16. More likely it's going to be 0.7, 0.3, 0.1. But you can think of this log of the probability as a measure of cost. This number of bits necessary to encode a message is intuitively just a measure of cost. It's a value that represents the cost of a test. And I'll leave it at that for now. If I take the probability and I multiply it by its cost, and this is absolute, I prefer the absolute value sign versus -1. If I take a probability and I multiply it by its cost, and I sum over all of these probabilities, notice that this probability is the probability of being a member of one class, say C1, given the value of the variable that I'm using to decompose the decision tree. So we'll come to this a bit later. But in fact, let's go to the example slide now. The context in which I'm going to be using this is to select the best divisive attribute, the best attribute in a current context for dividing a decision tree. And so I'm considering, is the best attribute some v sub I with values v sub I1, v sub I2. So in turn, I'm going to consider all the variables that exist, v1, v sub 2, v sub 3, v sub 4, v sub 5. And I'm going to be computing this expression on each of them. And this could be the case where, for example, the probability, what is the probability of renting it or watching a movie given that it is a sci-fi movie? Yes or no? What is the probability of watching it given it's not a sci-fi movie? What is the probability of renting it given it's something Ebert does not recommend versus does recommend? So in the movie example, each of these variables corresponds to variables that you've seen before in the decision tree. Each of these conditional probabilities comes with a cost, which again is just expressed in terms of, you can think of number of bits if you want, but it's just the log of the probability. And so it turns out that lower probability events will be associated with bigger costs, bigger logs, or bigger, I should say, bigger absolute values of the logs. So here's a sample of what we are given in deciding whether to decompose based on V1, V2, V3. And again, I don't show you what these values actually are. This is just an example. But in this case, again, this is a measure of cost. Summing over here is the expected number, the expected cost that I incur if I use a particular attribute's values to predict class. And then the probability of each of those values is important in predicting the expected number of the expected cost necessary to make a prediction on CK based on the other attributes. And so this is the same expression evaluated for different attributes. In this case, let's say that the probability of each value for V sub I, or V sub 1 in this case, is 0.5. So 0.5 times its own summation. In the case where V sub I equals V sub I1, and then in the case where V sub I equals V sub I2. Each of those probabilities is multiplied by the sum, where this is the probability in the case of V1, And this is the cost in the case of v sub 1. The absolute value of the log of 0.5 is going to be 1. And if we compute that, we get 1. Now notice that this function is to be minimized. And 1 is the very worst value you can get here. What does this represent? If you look at this case, it looks like the information utility of v sub 1 is minimal. If the value of v sub 1 is v sub 1, 1, that means that half the items within that subpopulation are going to be 0.5. If it's v sub I2, half of the data items in that subpopulation are going to be another class. So this is essentially saying that v sub 1, 1, even if you can identify the values of v sub 1, 1, your prediction is going to essentially be a coin flip. Okay? A fair coin flip. It will be one class with 50%, it will be the other class with 50%. And this particular example, that will be the case for both possible values of v sub 1. Okay? So in general, a variable that gives you something that is equivalent to a coin flip is a informationally impoverished variable. It's not something you want. On the other hand, at the other extreme is a variable that gives you a perfect prediction. Here, if, let's say that, again, just for the sake of the example, each of the variables' values are equally likely. But in the case where it's v sub 1, all 100% of the data there, in the case of v sub 1, are a member of one class. 0%, probability 0, are going to be members of the other class. And I just say here, for the sake of computing this, assume 0 times log 0 is 0, and we would assume that there. And so this is going to be a value of 1, or this will be a value of 0. And this will also be a value of 0, because in this case, in the case of the other variable, it's also a perfect predictor of a different class. And so the values of v sub 5 in this example apparently perfectly predict the classification. That is associated with one of the values here is a prediction of class 1. Associated with the other value here is a perfect predictor of the other variable, or the other class, rather. And so this is going to give us our minimal value of 0. So this will happen whenever you have 0 is the very best you can do in this case, and it is going to be a variable that gives you pure classes. Most of the instances are going to be in between. And so these are some instances you can study that are all in between. One of the variables may do a reasonably good job of predicting one class versus the other class. But the other value for this variable is not such a good predictor. In this particular example, each of the values of the variable that we're looking at is a pretty good predictor. In this case, v sub 1, 1 predicts class 1 with high probability, and v sub 1, 2, or v sub 3, 2 predicts class 2 with relatively high probability. And then this just goes to illustrate that not all the probabilities for the variable values have to be equal. You can have one high probability value which leads to very good predictions, and a lower probability value that leads to decent predictions. And that's going to fall somewhere in between 1 and 0, 2. So you can go through those examples, verify them, and it's possible I'll ask you about this function later. But the important thing, at least the intuitive thing I want you to get, is that is the big picture on attribute selection. If the variable that you're considering is statistically independent of the classification, then it's a terrible variable to predict. It buys you nothing in terms of prediction accuracy. If each value, in contrast, is associated with exactly one class, then that is a variable that we most value. And then most cases are in between. This is just an alternative measure that you could use for selecting attributes. In this case, you'd select the maximum.